So my slides are visible, right? Okay. So welcome you all to this second week of this tutorials for this NPTEL course is study guide in organic retrosynthesis problem solving approach. So this course, the instructor of this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban Maiti, so one of the TA for this course. So coming to today's talk, so basically, in each week I will explain, like I will show some introductory part related to organic synthesis, and then I will go detail about retrosynthesis. So basically, 2 3 slides I will discuss the introduction part, and then I will go to the mm, retrosynthesis part. Some examples we will discuss in each class. So, so if you see, yeah. So this classification of organic synthesis. So organic synthesis typically it was so it is classified into two parts. One is target oriented and another part is methods oriented. Now what is target oriented? So target oriented mean your target is fixed and you are doing the synthesis to complete that target molecule. Okay. So so total synthesis is one of the so it is an part of target oriented synthesis. Yeah. So, so target-oriented synthesis can be further classified into natural products and design molecules. Natural products means like whatever isolated molecules, like those were isolated from natural source. So that can be a part of target-oriented synthesis. Like here in natural products, mean the target is fixed, so we have to do the synthesis, we have to complete the synthesis. So that, so natural products synthesis comes under this target oriented synthesis. Also design molecules, like so like some material science interesting molecule, biologically interesting molecule, or medicinally interesting molecule. So so people from materials science background, so they want maybe some molecule for their research purpose, right? So for that purpose they can design a molecule and they can do the target oriented synthesis. Similarly biologically or medicinally, so if you think some molecules are mean some molecules may show some uh, biological activity or medicinal activities, then you can synthesize, and then after synthesizing those molecules you can do the biological studies or medicinal studies. Okay. So this is the part of this target oriented synthesis where your target is fixed. You fix your target and you are doing the synthesis to complete that target. Okay, right. So another part is methods oriented. So methods mean, so like reagents. So maybe you are dealing with some reagents, right? Like Wittig reagent, Grignard reagent, some oxidizing reagents. So you are doing so you are uh, dealing with some particular reagents, and you are doing where you are carrying, like you are carrying out some reactions by those reagents, and you are observing that how the reagents are working, like that. Catalyst mean, there is you are dealing with only catalyst. So you have to take you have to check whether the catalytic system is good or not, or like, so like that you can do the methodology on catalysis. Also synthetic strategies and synthetic tactics. So the right side are basically methodology related organic synthesis, right? And left side is target oriented organic synthesis. So this is if you see on book by Casey Nicolau and his student EJ Sorensen. So they have written one book, classics in total synthesis. So in that book they have clearly mentioned about these terms. Okay, so now come to the next slide. So I will show some landmark synthesis from 1828 to 1944. Okay, so as I discussed in last week, so urea was fast synthesized organic molecules. Okay, so and it was synthesized by Frederick Holler in 1828. Okay, so this is the fast synthesized molecule. So it was done by Holler in 1828, and then so acetic acid, all of you know. So Kolbe in 1845, he uh, he has synthesized this acetic acid in 1845. Okay, now Emil Fischer. Okay, so he's famous in sugar chemistry. So he also synthesized this glucose in 1890s. Okay, so you can see how in those 18th century or 19th century how they are synthesizing those molecules. Okay, you can see the chirality also. More of like many molecules are having more chiral synthesis, right? So like alpha terpineol, Parkin, Parkin condensation reaction, that Parkin, Dr. Parkin, he has synthesized this alpha terpineol in 1904. Camphor also, camphor mainly it's used in puja purposes. So Parkin again in 1904 and Compa in 1903, they have synthesized this camphor. Also another molecule tropinone. Okay, so in 1917, Robinson, he has synthesized this molecule. So Robinson mean Robinson annulation. I guess you heard. So that Professor Robinson, so he has synthesized this tropinone. Okay, so like that, Fischer again, he has synthesized in hemine in 1929. Then equilenin by Batchman in 1939. Also, I have shown in last week Professor R.B. Woodward. So he has synthesized the quinine molecule. Okay, he completed the formal synthesis of quinine molecule in 1944. Okay, so like that, you can see a glimpse of many molecules how people have synthesized in between 1828 to 1944. So basically this will grab the attention from synthetic chemists to do more synthesis in this background. 1 minute. Yeah, so just a second. uh, can you please mute Sudeep? Yeah, thank you. Okay, so I will start again. So those who joined now, so here you can see so some beautiful synthesis in between 1828 to 1944. From the beginning of this 1820, from the beginning of this synthesis was done by Holler in 1828 from urea synthesis. Okay, so like that, many molecules have been synthesized in this duration. Okay, so now I will come to the next slide. So in this slide, yeah, as you can see, so Professor Casey Nicola. Okay, so oh, sorry. Can you see the slides now? Okay, thank you. So, Professor Casey Nicolau. So, he was at Scripps, USA. Also, he was at Rice University. So, he's a very famous organic synthetic chemist. Okay, and he has completed the total synthesis of several molecules, which are medicinally active as well as biologically active. Mm, so he is a famous organic chemist. So one of the quote I have written here, like, persist and withdraw when you are faced with difficulties, so redesign and strategies and try again. Okay, so this is the famous quote by Casey Nicolau. Okay, so now if you see these two molecules, okay, so this molecule is highly complex molecule. If you see, this molecule is having total in the core, this is the core structure. Okay, so a, this is called A ring, this is B ring, this is C ring and D ring. Okay, so A is 6 member ring, and this B is 8 member ring. Okay, and the C ring is 6 member ring, and D, this is oxygen ring, 4 member oxygen ring. Okay, and you can see how many chiral syntheses are there in this molecule. Okay, so synthesize to synthesize this molecule is really challenging, and this molecule, the name of this molecule is Taxol. Okay, and this is a natural product. Uh, mm, so it was isolated by Professor Halton group, I guess, not sure. Now they have completed the total synthesis, like Casey Nicolau group. So their group, they have published the total synthesis of this molecule in 1994. Okay, and this molecule is a anti-cancer drug. Okay, and the commercial name of this Taxol is paclitaxel. Okay, so this molecule is highly like, it has huge role in pharmaceutical industries. So this paclitaxel is used as a anti-cancer agent, and also it used to treat this Kaposi sarcoma disease. Okay, so one type of cancer disease, you can say. Also, they have synthesized this molecule. This is called, so this right side, if you see this molecule, if you see, this is a very big molecule, also having many so highly oxidized framework. Okay, so to synthesis this molecule also not an easy task. So this is also a challenging molecule. So this molecule is eribulin. Okay, so Professor Casey Nicolau group, they have synthesized this molecule in 2022. And so the story for synthesize so for the synthesis of eribulin, there is a story like eribulin not a it is not a natural product, rather it is a synthetic drug. Okay, so if you see the drug analog, so this halaben is a commercial name. So it is basically the mesylate salt of eribulin, look like NH2 dot methane sulfonic acid, MSOH. Okay, so that is halaben. So commercially, halaben is used to treat this breast cancer as well as liposarcoma. Okay, so eribulin, it is not a natural product, rather it is a synthetic drug. Okay, so there are molecules with helicondrin series natural product. Okay, helicondrins are naturally occurring, like it is isolated from nature, and helicondrins, it is also having this left hand side part. Okay, but right hand side part is different. Okay, uh, now while the synthesizing while doing total synthesis of helicondrin B, Professor Kisi group. Okay, Kisi is an Professor Kisi. He is an another organic chemist. He also and famous organic chemist. Okay, Professor Kisi group. They have synthesized that helicondrin B natural product. Okay, and they have collaborated with National Cancer Institute. Uh, and to see the biological activity of that helicondrin B natural product. Now, interestingly, they found that Heliconium B is not having that much biological activity, but this part, so with this part na, so it is showing, if it is having this part, so it can shows cancer activity. So by that idea of Professor Kisi group, they have synthesized, like they have planned this molecule and they have synthesized this molecule, and they, when they check the biological activity, they got to know that it is an anti-cancer agent, and it is a huge important so it is like a highly useful molecule. Okay, so like that, Professor Kisi group first synthesized this eribulin, and later in 2022, so recently Casey Nukalau group also they have synthesized this eribulin. Okay, and halaben and it is used as a halaben in market, and halaben basically it is an methane sulfonic acid salt of this eribulin. Okay, so like that, Professor Casey Nicolau group have synthesized many many natural products or unnatural products. Those are having biological or medicinal importance. Okay, so you can get an idea. So you, I guess you got an idea how molecules can show various bioactivity or medicinal activity. So that is why we have to focus on the synthesis part, and we have to do the synthesis. Okay, if you don't do synthesis, then how you will get to know about which molecule can show bioactivity or not. Okay, so that is why synthesis is important. It is an relevant um, part of chemistry. Okay, so now this is the introduction part. So I will come into the details of retrosynthesis. Okay, so this is our topic of discussion. So I guess Professor Samik Nanda, he has already, if you follow his uh, videos, he already discussed about target molecule, that is TM or TGT. You can say TGT or TM. So target molecule in retrosynthesis, you will have some target molecule, and you have to do the disconnection, like carbon carbon bond disconnection, or some functional group interconversion or addition. So by that you have to do the retrosynthetic analysis. Okay, so now we have this molecule. Okay, so it is having one carbonyl group and one olefin side chain. Okay, how we can plan to synthesis this to synthesize this molecule. Okay, so let's say we can think about this CC bond disconnection. Okay, so this arrow is for CC disconnection, to show the CC bond disconnection. So if we talk about this CC bond disconnection, so what we can think. So basically, this is the retrosynthetic arrow. We already discussed about this, and so after this CC bond disconnection, what we can get. So if we disconnect this CC bond heterolytically. Okay, heterolytically mean this bond, this CC single bond is having two electrons, right? So heterolytic cleavage mean, so one carbon can take two electrons from this bond, and another carbon will be positively charged. Okay, right? So like here, this carbon is taking the two electrons from this bond, and this carbon is getting positive charge, and as it is having two electrons, so it is showing negative charge. Okay, so now if we, when we do this retrosynthetic analysis for this CC bond disconnection, so we are getting this it's like charge species, but so this charge species we are getting, and this charge species we can call as syntones. Okay, syntone. Now it is having negatively charged, so we can call as donor syntone. Like, why donor? Because it can donate the electrons, and it is having positively charged, so it can accept the electrons. So it is called acceptor syntone, right? So now, when we'll do the forward synthesis, like from here to here, back forward direction, if we when we'll do, so we can start with this charge species, right? So we have to take some neutral species. So for that, synthetic equivalence comes. Okay, so this is the donor syntone, and this is the synthetic equivalent of donor syntone. So when we'll do forward synthesis, we can use this uh, and this. And what is this? So this is the synthetic equivalent of acceptor syntone, right? So how this charge, if you see this charge, this is uh, alpha to this carbonyl, right? So alpha to this carbonyl, we can so this carboanion, alpha carboanion, we can easily generate from this carbonyl compound if we treat any base. Okay, if we treat this compound with any base, then we can easily get this carbanion. Okay, so this donor synthene. And if we are having this C halogen bond, okay, so this, because of this electronegativity of this halogen halides, so this CX bond, if you see the polarity, so this will be the delta negative, and this carbon will have delta positive. Okay, so that means it is, this carbon is electropositive here, and this carbon is, like, we can generate negative anion, negative charge easily from this ketone, right? So this is called synthetic equivalent of donor syntone, and this is called synthetic equivalent of acceptor syntone. Now we'll show in detail like how we can do the CC bond disconnection, right? So CC bond disconnection we can do by three different ways, right? So we can do the heterolytic cleavage and homolytic cleavage and concerted transform. Okay, heterolytic cleavage mean this CC bond is having two electrons, right? So one carbon can take two electrons of this bond, and another carbon, then it will show the positive charge, right? So, and also it can be vice versa, right? So like this carbon is having two electrons, so this is negative, and this carbon is having no electrons, so positive. Or it can be like this carbon could show flow positive, or this carbon may show this negative, so it is having two electron now. So this is by heterolytic cleavage we can think about CC bond disconnection. Now homolytic cleavage mean, so it is having this carbon carbon bond is having two electrons, so both carbon is taking one electron. Okay, so this is called homolytic cleavage. Now, so basically in radical chemistry we can think about homolytic cleavage. In So only in radical chemistry we can think about homolytic cleavage. Most of the cases we will see the heterolytic cleavage only. Okay, and concerted transform mean, the transformation don't involve any positive or negative charge species. Okay, so it is concerted like Diels-Celler reaction. Okay, so this is the diene and this is the dienophile. Okay, so this is concerted, this yeah, this is concerted mechanism, like this will fall here, and this, so this is the concerted mechanism. So this arrow push mechanism. Okay, so like that, like this we can think about CC bond disconnection approach. So most of the cases we will see the heterolytic cleavage. Okay, yeah. So now so coming back to this heterolytic cleavage again. So heterolytic cleavage, if we do, uh, so we can get this donor syntone, so which is having two electrons. So electrons now will not show electrons anymore, so negative charge mean it is having two electron. Okay, and this is acceptor syntone, so it is not having any electron, so it is positively charged, so acceptor syntone. And this is negatively charged, so it is donor syntone, so it can donate the electron and it can accept the electrons. Okay, so now donor syntones, we'll see how how many types of donor syntones could be there. Okay, and we'll see the synthetic equivalents with respect to those donor syntones. Also we'll see some acceptor syntones and synthetic equivalent. So if we think about this donor syntone, like alkyl anion. Okay, like carb anion. Okay, alkyl anion mean basically carb anion. Okay, so alkyl anion, how we can get. Okay, so the synthetic equivalent is Rx, but Rx, R is electropositive, and X is R is delta positive, X is delta negative, right? So, but we have to generate this alkyl anion. How we can do? So, Rx is the synthetic equivalent, but we can make an reagent, that is this magnesium pieces or lithium pieces. Magnesium mean Grignard reagent, or alkyl lithium pieces. Okay, where this metal will have positive charge, and so magnesium and lithium will have positively charged, and this R will show the negative, like delta negativity. Now, so from those reagents we can get this alkyl anion. Okay, and if we talk about the cyanide ion, okay, so this is the donor syntone. How we can get from NaCN, okay, and the synthetic equivalent is HCN. Also, if we talk about acetylide mean the CC. So if you want to generate the negative charge at carbon carbon triple bond, okay, so this is the synthetic equivalent. It is having this CH, so acetylenic part. Now, if you treat with this acetylene with butyl lithium, okay, any alkyl lithium, butyl lithium, n-butyl lithium, or tertiary butyl lithium, so you can get this. So butyl lithium can take proton from this carbon, and it can give this C minus Li plus species. Okay, now this is C minus, so this is acetylide. So you can generate acetylide from this alkyne. Okay, also if we talk about enolate mean, so enolate basically it has two reactive sites, and one is this O minus can act as a nucleophile, also this carbon can act as a nucleophile. Now this enolate, how we can generate? So the synthetic equivalent should be this carbonyl compound, right? Now if we treat this carbonyl compound with any base, uh, LDA or sodium hydroxide, sodium methoxide, we can generate the metal enolate, right? So metal enolate we can generate. So this is the reagent, and this is the synthetic equivalent. Now, if we talk about elide, so elide mean this we take elide generally. So this elide, how we can generate? So we can generate. So by taking this synthetic equivalent, so this is R halide. Okay, so if we treat this compound with ppH3, so it will do some simple SN2. So and it will give this Wittig salt. So this is the Wittig salt, and if we treat this Wittig salt with base like potassium tertiary butoxide or n-butyl lithium, then that base will take this proton, right, and it will generate this elide. So you can get idea how we can generate this donor synthon from their respective synthetic equivalents. Also, if we see this acceptor synthon, that is R plus, okay, R plus mean alkyl cation. So how we can generate? So Rx. So synthetic equivalent is Rx. So Rx mean R is delta positive, X is delta negative, because halogen is having electronegativity, more electronegative elements halogens are. Okay. So when from Rx you can get this alkyl cation directly, but here you see from Rx, if you treat this Rx with magnesium, you will get RMGX, and you get the reversal of polarity. Okay, you are getting now R minus from Rx. So via magnesium insertion, you can get this opposite donor syntone. Okay, okay. Now if we talk about this acylium ion, okay, acylium ion, how we can get? So this is the carbonyl center, carbonyl carbon having the positive charge. How we can get? So from this RCOX, where X could be Cl or amine or methoxy. Okay, so now if we want to get this is the alpha beta unsaturated alpha beta. So this is alpha carbon, this is beta carbon, right? So if you want beta positive charge next to this carbonyl group, how we can get? You can get easily from this alpha beta unsaturated carbonyl compound, right? So alpha beta unsaturated carbonyl compounds, so this double bond can resonate, can do resonance with this carbonyl, and it will show this delta positive, right? So it will show delta positive at beta carbon and delta negative at alpha carbon, okay, and this carbon is delta positive, so you can easily generate this carbocation. Now if you want to generate carbocation next to alpha to this carbonyl group, then you can easily have this alpha bromo ketone compound, or alpha bromo or alpha chloroketone compound. And this in this compound you can easily generate this donor acceptor syntone, okay. And if you have this mm, beta positive charge with respect to this OH, okay, how you can generate? You can generate simply from epoxide, okay. So by epoxide ring opening, so this ring can open, and you will get the positive charge here, okay. So now, you got an idea how we can get the synthetic equivalents for both donor synthon and acceptor synthon, right? So now we'll go to the our previous problem. So we were talking about this problem, and we did this CC1 disconnection approach. So this is heterolytic cleavage. So heterolytic cleavage, basically we were thinking about this donor synthon and this acceptor synthon. Now this donor synthon we can easily get from this carbonyl group, because we can easily generate carboanion from this carbonyl compound. And how we can get this acceptor anion, acceptor synthon? So if we have this C iodine bond or C bromine bond, we can easily get this acceptor synthon, okay. Now coming to the forward synthesis, how we'll do the reactions to get this. So how we can get this our target molecule from this synthetic equivalence? So we'll see the forward synthesis now. So forward synthesis, we have to take this carbonyl compound, right? So this is having proton now at alpha position. Now LDA is base, right? So LDA is base, lithium diisopropyl amide. So LDA at minus 78 degrees centigrade. So it will generate kinetic enolate. So here is only one possibility. Both sides will get same enolate. Okay, so no worry. So you will get this enolate. So basically lithium enolate you will get. Okay, so lithium. So LDA is lithium diisopropyl amide. So you will get this lithium plus, so and O minus. So this is the ion pair and this enolate. So lithium enolate you will get. Now if we add this alpha iodo compound, alpha iodo keto compound, so it will, so how it will react? So this minus will fall, and this enolate will attack to this carbon center, right? And normal substitution will happen, and you will get your desired target molecule. So this CC bond is forming in this transformations, okay. So this is a simple example. Another simple example we'll see, right? Yeah. So what is happening here? So this is the compound, one, two, three, four. Yeah, this carbonyl compound. So if we think this CC1 disconnection approach, okay. No, no, not first CC1 disconnection approach. First, we will see the functional group interconversion. So it is having this carbonyl group, right? So we can think about this. So alcohol, okay. So this, if you do oxidation of this alcohol, so in forward synthesis, if you do oxidation, okay, then you can get the carbonyl compound. Now, so this is the functional group interconversion. So now if we think about this CC bond disconnection approach, okay, so what you will basically get, so uh, this is the donor synthon. So this is negatively charged, so this is donor synthon, and this carbon is having positive charge, so this is the acceptor synthon. Now, so this donor synthon, from where it will get, where it will, from where we can get, right? So this is the basically carbanion or alkyl anion, okay. Alkyl anion already we saw the alkyl anion. So yeah, this alkyl anion we can get from Grignard reagent or RMGX or RLI, okay. So Yeah, so we can, so this propyl anion we can think about the synthetic equivalent, not synthetic equivalent. So this is the reagent. So this is the propyl magnesium halide. Okay, so we can think about this reagent, and this reagent can be derived from this synthetic equivalent. Okay, propyl halide. So this is the synthetic equivalent for donor synthone. Now this acceptor synthone, so this is the positively charged. How we can get? So basically, if we think about this carbonyl, like basically benzaldehyde. So benzaldehyde, we can get easily this acceptor syntone. Just a minute. Yeah, my slides are visible, right? Okay, thank you. Yeah. So you can see how we can do the retrosynthetic analysis for this target molecule. Okay. So there is another way to get this molecule. Like we can do, yeah, we can think about the functional group interconversion of this molecule, and we can get this alcohol, right? So now we can think about this CC bond disconnection approach. So what we will get? So we'll get this side, basically this side positive charge and this side phenyl negative charge. Okay, so phenyl negative charge, and this side it is having one, two, three. Yeah, so this side it is acceptor syntone, right? So this is the positive charge. So acceptor syntone we can easily get from this corresponding aldehyde. So one, two, three, four, butanol. Okay, so we can get from butanol. So this butanol and this donor syntone. So phenyl minus we can easily get from phenyl grignard, right? Phenyl magnesium bromide. So this like this also we can do the disconnection approach, right? And okay, so we can get the 2cc1 disconnection approach now, basically. So in next slide we'll see the forward synthesis to get to complete this molecule. Okay, so basically we have to take this one, two, three, yeah, profile bromide, and if we do the magnesium insertion, make that means if we make this Grignard reagent. Okay, so Grignard reagent, how we can make? So basically you have to take magnesium turnings, magnesium 0 pieces, magnesium turnings, and you have to take catalytic amount of iodine. Okay, I will tell you the role of iodine. Also you can yeah, and also you have to take solvent. You can use THF, tetrahydrofuran, or diethyl ether. You can use any of the solvent. Okay, so basically magnesium it is inserting between this CBr bond. Okay, that's by that you can get this Grignard reagent. Now what is the role of iodine? Okay, so this magnesium insertion is happening via radical process. Okay, so this preparation of Grignard reagent, so it is happening via radical process. Okay, so now if you have magnesium turnings. Okay, so that magnesium turnings, so it has the metal has its surface area, right? So it's in its surface area. So sometimes magnesium oxide can form by aerial oxidation. Okay, so like uh, mm, aerial oxidation by oxygen, like aerobic oxygen. So magnesium surface oxidation of magnesium surface can happen, and like magnesium oxide could be there in the magnesium surface. Okay, so now this iodine, people used to use very catalytic amount, like small amount. Okay, so this iodine can remove the magnesium oxide from magnesium surface, and it can activate the magnesium surface basically. Okay, so yeah, so that is so by that you can prepare this Grignard reagent. So this is a propyl Grignard magnesium bromide. So you can generate this magnesium magnesium, so this Grignard pieces. So now this Grignard pieces, so as you all know, so this is the negative, this carbon is negatively charged, delta negative, and this magnesium is having delta positive charge. Okay, and this is having delta negative. Yeah, so now it can easily add to any electrophile. So we are using this benzaldehyde as a electrophile, right? So this carbon will add to this benzaldehyde, and it will form this O minus. So basically not O minus, so OMgBr. Okay, so O minus and its counter cation is MgBr, O minus and MgBr. Okay, so that we can do the work of by treating with H3O plus, and we can get this alcohol, right? So now if we do, so this is basically oxidation, alcohol to ketone. So if you see clearly, uh, if you see properly, so you can see, you can tell that this alcohol is benzylic. Okay, so benzylic oxidation could be done by using MnO2, manganese dioxide, or also you can use DMP or PCC. You can for converting this alcohol to ketone. Okay, yeah, so that is how you can get this alcohol to ketone. Okay, so I guess you have got some idea how you can prepare Grignard reagents in laboratory. Okay, so sometimes some Grignard reagents are available, or sometimes it's not available commercially, it's not available. Okay, so that time you have to prepare by your own. Okay, and if you know for clearly how you can make, so then the job is done for you. Yeah, so now come to the next retrosynthesis. Yeah, this terpineol. Terpineol, as I have already shown the structure of terpineol in my third slide today. So terpineol was so this molecule was synthesized by Parkin. Okay, Parkin. So this terphenyl is a six-member molecule. Okay, so six-member cyclohexene type of molecule. So basically, if we if we talk about cyclohexene, then and if we do the retrosynthesis, so the first thing will come to your mind that you can do Diels-Cellar reaction to get this cyclohexene type of intermediate, right? So Diels-Cellar reaction mean you have to use this diene and this dienophile. Okay, so this is the concerted process. I already told you. Yeah, concerted process to get this 4 plus 2 cycloaddition. So simply if you hit this diene and dienophile, you can get this six member ring. Okay, easy. Now this dienophile, so how you can get, so if you see this dienophile, it is having this tertiary alcohol. Okay, so tertiary alcohol, so this is the dienophile. How you can get, so functional group interconversion from this methyl acrylate. Okay, so this is the molecule called methyl acrylate. So basically it is alpha beta unsaturated ester. Okay, so if you treat this ester with two equivalent of Grignard reagents, MEMGBr, so you can get the addition of methyl two times, right? Twice addition of this methyl to this ester, you will get this tertiary alcohol, right? And this methyl Grignard, as you know, how you can get, so you can get from methyl bromide or methyl iodide by treating with magnesium, right? In previous slide only we have discussed magnesium. Okay, now so here is, if you do the forward synthesis in this, for this retrosynthetic for this specific retrosynthesis, if you do the forward synthesis, so So you will get methyl magnesium bromide from methyl bromide easily. Then you can get this tertiary alcohol easily. Now the problem will appear here. If you do the When you will do the Diels-Sala reaction, so this dienophile is not that much activated, right? So we know that dienophile should be electronically so like electron deficient dienophile are good, okay, for Diels-Sala reaction. Okay, now here the dienophile is not that much electron deficient. Okay, so instead of this dienophile, if we interchange this dienophile, okay, so if we use this dienophile, this methyl acrylate, this Diels-Sala reaction is very fast now. Okay, so now we will plan our retrosynthesis. Okay, so as you can see, so fast we will do this Diels-Sala reaction with this activated dienophile to get this cyclohexene. And then we if we add this methyl magnesium bromide to this ester, two equivalent of methyl magnesium bromide, so you will get this tertiary alcohol, right? So you can get this terpineol. Okay, right? So you can easily get this um, terminal molecule from this two building blocks, right? So these two synthetic equivalent. So now as this is Diels-Sala reaction, so there is no heterolytic cleavage, right? So there will be no synthons kind of things. Okay, so there is no synthons. So this is like concerted mechanism, so only starting metal you can get. So now the forward synthesis. So if you see the forward synthesis, first you have to take this diene and this methyl acrylate as a dienophile, and if you heat this mixture, okay, so you will get this CC bond. Okay, this CC bond is newly formed, and this cyclohexene. Okay, so basically yeah, this you are getting this cyclohexene, six member cyclohexene ring. So now your job is almost done. You have to do convert this ester to tertiary alcohol. So you can easily do by treat this ester with two equivalent of methyl magnesium bromide, right? So and this methyl magnesium bromide, as you all as you know, it can be derived from methyl halide. Okay, halide mean basically bromide or uh, methyl bromide or iodide. Okay, so if you take magnesium turning and in diethyl ether solvent, you will get this methyl magnesium halide. Okay, so you can see how Diels-Sala reaction plays an role to care to construct this six member cyclohexene type of intermediate. Okay, so from that you can do anything to get your desired product. Okay, yeah. So now next slide. So we will talk about this specific molecule. Okay, so retrosynthesis. We If we think about the retrosynthesis of this molecule, okay, what we can do. Okay, like what we can do with this molecule. So if you see this molecule properly, so this is having this tertiary alcohol, right? So and no other functional groups are there. Okay, so we can easily think that this CC bond disconnection approach. Okay, this CC bond we can easily break, and we can see the disconnection approach by utilizing disconnection approach, what type of synthons we can get and what type of synthetic equivalents we can get. All right, so this CC1 disconnection approach, you will get basically this synthon. So this is the positively charged alcohol. Mm, so this is called acceptor synthon, and this carbon is bearing this negative charge, so this is called donor synthon, right? So this acceptor synthon, from where you will get, so basically from this cyclopentanone. So because this cyclopentanone so this carbonyl carbon is having a delta positive charge, so you will easily get this positive charge here. And also this anion, so basically this is carbanion mean you can easily get from Grignard reagent, right? Grignard reagent. So this is the reagent So this is a this Grignard reagent we use, then we can get uh, this conversion. Okay, just a minute. Yeah. So now, so this cyclopentanone is fine. So this is a synthetic equivalent for acceptor syntone. Okay. Now what? How we can get this reagent? This Grignard or Grignard reagent? How we can get? So if we think about this Grignard reagent, you can get easily from this R bromide, right? So this alkyl bromide, we will get this reagent, Grignard reagent, right? By treating with magnesium we can get this Grignard reagent. Now from where we can get this synthetic equivalent? So this is basically synthetic equivalent of this donor syntone. So this is the donor syntone, and this is the synthetic equivalent of this donor syntone, right? So basically, synthetic equivalent, if we treat with Greek magnesium, then we can get this reagent, and this reagent. So this is the synthetic synthons. Okay. Now, from here we can get this alkyl bromide compound. So basically, we can get this alkyl bromide compound from this alcohol by doing some Appel reaction kind of things, right? So just a minute. Yeah, slides are visible, right? Yeah. So now this alcohol compound, how we can get? So we can get like if we do this CC1 disconnection, right? 1 minute. Yeah, if we think about this CC bond disconnection, okay. So this is delta positive or this is delta negative, right? So that means this is positive and this is negative. So these symptoms we can get, okay, and this. So this is alpha carbon and beta carbon. So beta to this. So beta positive charge alpha like to this next to the alcohol we can easily get from the epoxide. Okay, so from epoxide we can get this synthon. So and this is the synthetic equivalent. So synthetic equivalent is this epoxide, and this as donor synthon. So basically again this is a carbanion, and we can easily get from this magnesium pieces, that is called Grignard reagent, and this Grignard reagent now we can get from this synthetic equivalent. Okay, so this is the synthetic equivalent. So alkyl halide, alkyl bromide compound. Again, you can think how you can get this alkyl bromide compound. So from the corresponding alcohol, if we do Appel reaction, we can get the um, we can get the we can get the alkyl bromide compound. So if you think like this, um, so this is the corresponding alcohol. So if you do Appel reaction, you will get this bromide compound. Now from how we can get this compound? Again same, okay, this CC1 disconnection approach. Okay, so this CC1 disconnection approach, if we do like, so again this is positive charge and this is negative charge. Okay, so this positive charge, as you can see, this can be derived from epoxide. So epoxide, and the negative part you can derive from the corresponding Grignard reagent, right? So this is isopropyl magnesium, um, isopropyl magnesium bromide. Okay, so this Grignard reagent, if we treat with this epoxide, then we'll get this alcohol compound, and if we do Appel reaction we can get synthetic this bromide compound. Now if now this molecule this halide already commercially available. So we no need to do further disconnection approach. Okay, if it is not available, then we can think about this disconnection approach. Okay, so for showing purpose, I just drawn the further disconnection approach. For you can get uh, more understanding to this disconnection approach. Okay, now okay, now coming to forward synthesis. So forward synthesis, as we already discussed, we have to take this alkyl bromide compound, and if we treat this alkyl bromide with magnesium and iodine, catalytic amount of iodine, and in diethyl ether, so we can easily generate this Grignard reagent, right? So already I have told you the role of iodine uh, in the preparation of Grignard reagents, right? So this Grignard reagent, if you treat with this epoxide, so basically this carbon is delta negative. Okay, so this will open up this epoxide, and you will get this alcohol after acidic workup. Okay, H3O plus. So basically after opening you will get OMgBr, right? O minus and Mgbr plus Mgbr as its counter cation. Okay, so and if you do the workup, you will get this alcohol compound. Okay, now we have to convert this alcohol to halide, right? Bromide. So if we treat with this alcohol with PBr3, we can easily get this RBr. So alkyl bromide. Again, we have to make this Grignard reagent by treating this alkyl bromide with magnesium, and we can get this Grignard reagent. So now finally, if we add this Grignard reagent to this cyclopentanone, right? This carbonyl compound, we will get this tertiary alcohol. So now you can see how we can do the retrosynthesis and how we can do the forward synthesis for many molecules. Yeah. So just a minute. So now coming to the next molecule. Yeah. So this is very interesting molecule. I guess all of you know this flower. So this is called jasmine flower, and from this jasmine flower, so the one of the volatile component of this jasmine flower is jasmine. Okay, and all of you know jasmine is having good odor. Okay, like it is used as a fragrant. Also it has frag, uh, in pregnant industry they use jasmine, right? So this jasmine is having very good smell. Okay, and so it is one of the volatile component of jasmine flower. So this is the jasmine flower. So this jasmine, if you see the structure, this jasmine is having, so what type of functional groups it is having? So basically one carbonyl group is having, and if you think about unsaturation, so it is having this CC double bond. So yeah, so tetrasubstituted double bond, and this is C solipine. Okay, disubstituted C solipine. So how you can plan the retrosynthesis for this jasmine molecule? Okay, very interesting. So this is our target now. So TGT or target molecule, and if we do the functional group interconversion, right? So of this double bond. Okay, so this molecule we can easily get from this alcohol, tertiary alcohol. So basically dehydration. Okay, acid or base mediated dehydration, if we do, you can get this alpha beta unsaturated carbonyl compound. So now if you uh, properly see, so this is alpha carbon and this is beta carbon. Now this is beta hydroxy carbonyl compound, right? So one of the way to get beta hydroxy carbonyl compound is aldol reaction. Okay, so basically if we do aldol reaction, then we can get this beta hydroxy carbonyl compound, right? So aldol reaction of this one, two, three, four, 1,4 diketone. Okay, so we can get this cyclopentane type of framework and this beta hydroxy ketone. Now further disconnection of this 1,4 diketone. Okay, so how we can do? So basically we can think about this CC bond. Okay, we can think about the disconnection of this CC bond. So what you will get? So this is Yeah. So this carbon is bearing electropositive charge, and this carbon is bearing electronegative charge. Okay. So this is the acceptor synthon, and this is the donor synthon, right? So these are two synthons. So this is acceptor synthon, and it is having negative charge, so it is donor synthon. Now this acceptor synthon, from where we can get? So what is the synthetic equivalent? So basically you having the alpha beta positive charge, right, to the carbonyl compound. So you can easily get from this alpha beta unsaturated carbonyl compound. So generally the beta carbon of alpha beta unsaturated carbonyl compounds are positively charged. Okay. So you can get the synthetic, so you get the synthetic equivalence of this acceptor synthon. Now what about this donor synthon? So donor synthon, if you see, this is acylium uh, carbanion. Okay. So this is acylium anion. So acylium anion, how we can get? So we can get from two pieces, this nitro ethane, or we can get from this 1,3 diethane. Okay. I guess all of you know from 1,3 diethane, if we treat this 1,3 diethane with NVTI lithium, we can easily abstract the proton, and we can generate the anion at this carbon center. Okay. And that can act as a nucleophile. Okay. So this is the one of the synthetic equivalent of this acylium anion. Another synthetic equivalent is that this nitro. Okay. So you can easily generate this carbanion pieces alpha to the nitro group. As you can see, the pK of this nitroethane is 8.5. Okay. So if you treat this nitroethane with with any milder base, so you can easily generate this carbanion. Okay. So also, if you take this 1,3 diethane compound, you have to take basically in vital lithium strong base. Okay. Yeah. So this is the Ompulang chemistry. Okay. So generally the carbonyl center used to be like used to be positively charged. Right now you are generating anion at carbonyl center, so you have to uh, do the Ompulang chemistry. Okay. So Ompulang chemistry. So by this two way we can generate the carbonyl anion. Okay. Now, what? So synthetic equivalent of this acceptor synthon, this is the alpha beta unsaturated ketone. Okay, so from where we can get this molecule? Again, this CC1 disconnection, this CC1 disconnection. Okay, so if we do this CC1 disconnection, you can get this positively charged species, and this is the negatively charged species, right? Now, so this is for this alpha beta unsaturated aldehyde. So this is the synthetic equivalent, and for this negatively charged species, so this is carbanion. Carbanion mean you can easily generate from this Grignard reagent, right? So this is the Grignard reagent, and this Grignard reagent you can easily prepare from corresponding alkyl bromide compound, right? So already we have discussed about Grignard reagents, how we can generate. Now, uh, coming to the next slide, that is yeah, that is forward synthesis, right? So in forward synthesis, first we have this Grignard reagent. So again, Grignard reagents we have to prepare. Already we have discussed how we can prepare this Grignard reagent. We have to take the corresponding alkyl bromide compound, and we have to do the insertion of magnesium in between the CBr bond, and we can get this Grignard reagent, right? So what we have to do now? So this Grignard reagent we are having now, and we are having this alpha beta unsaturated aldehyde, right? So basically we will do 1 2 addition. So it is having two reactive like center for nucleophile. So for nucleophile can attack as 1 2 fashion. So 1 2 fashion means this carbonyl center nucleophile can attack, or this beta carbon, beta to this carbonyl group nucleophile can also attack. Okay. Now if we do the 1 2 addition, so 1 for addition basically if you use copper 1 salt, that time 1,4 addition will happen. Now if you use normal Grignard reagent, so you will get this 1,2 addition product. Okay, so by 1,2 addition of this Grignard reagent to this alpha beta unsaturated aldehyde, you can get this secondary alcohol, right? So this is the allylic alcohol. Now if you do the oxidation of this allylic alcohol, so allylic alcohol, the MnO2 is a easy choice to do the allylic oxidations. Otherwise you can use PCC or DMP also to get the oxidation of this secondary alcohol. Okay, so you got this carbonyl group. Now again you have make uh, you make this alpha beta unsaturated ketone now. Okay, so now if we do the 1,4 addition of this nitroethane. Okay, so this nitroethane, already I have shown the pK of nitroethane is 8.5, right? So you can use this weak base sodium methoxide, so to take proton from the alpha to the nitro. So this hydrogen, okay, so this hydrogen, it can, sodium methoxide can easily abstract this proton, this alpha proton, and then 1,4 addition. So this negative charge, so this anion can easily attack to the 1,4 fashion. Okay, so Michael addition, basically Michael addition of this 1,4, Michael addition of this nitroethane, you can get this compound. So basically this CC bond is forming now, right? So this CC bond is forming here. Now if now we have to convert this nitro to ketone, right? So this is called NAP reaction. Already Professor Samik Nanda has discussed about NAP reaction. So many reagents we can use, like we can use some acidic conditions or basic conditions, or we can use some neutral conditions like TiCl3, titanium trichloride. So that is reducing agent. So carry out any we can carry out NAP reaction by using any of the conditions. Okay, so here we use 10 normal H2SO4 to get this conversion nitro to carbonyl group. Now the next part is that basically you have to do the uh, aldol reaction in order to get this alpha beta unsaturated ketone. So this is the 1 2 3 4 1 4 diketone, right? So one, this is number 4 carbon, right? So 1 4 diketone. So 1 4 diketone, first if you treat this with sodium hydroxide, right? Sodium hydroxide in ethanol solvent, and if you do the reflux, okay, if you uh, increase the temperature and do reflux, you will get the aldol product first. So aldol product mean first this enolate will generate, right? So this minus, so this enolate will generate. Now this enolate will attack to this carbonyl group, and you will get this 5 member ring, right? 5 member ring having this alcohol here. Okay, so basically alcohol you will get here. Now in same condition, dehydration will take place. Okay, in reflux condition dehydration will take place, and you will get this alpha beta unsaturated ketone. So this is the jasmine. Okay, so now you can get how we can synthesis, how we can do the synthesis of jasmine in laboratory. Okay, so this is easy synthesis. So you can see how easily you can make jasmine in your lab. Okay, so not only you can get from this jasmine flower, also you can prepare by yourself in your lab, and also you can take the smell. Okay, so this is the beauty of chemistry. So now coming to the last example of this today's uh, tutorials. So this is one of the molecule. If you see this molecule, if you see clearly, this molecule is having so this is a tricyclic molecule, right? So this is a 6 member. So this is aromatic part, and this is the 6 member ring, and this is the 5 member ring having alpha beta unsaturated carbonyl group. So this alpha beta unsaturated carbonyl group, from where we can get? So already we have discussed in last slide. So this alpha beta unsaturated aldehyde we can get via aldol reaction, right? So if we do the aldol reaction of 1,4 diketone, we can get this alpha beta unsaturated ketone, right? So similar way, so we are having this one, 2, 3, 4. So this is the carbon number 1 and this is the carbon number 4. Okay, so this 1,4 diketone we are having, and if we do this aldol reaction, so we can get this alpha beta unsaturated carbonyl compound. So this is our target here. Okay, so this is the TGT. So if you so this is the TGT of our retrosynthesis. So and what we are planning, first step, we are planning for aldol reaction, right? So aldol reaction we are planning in the first step after retrosynthesis, right? So aldol reaction of 1,4 diketone. First aldol reaction, intramolecular aldol reaction followed by dehydration. So we can get this target molecule TGT. Okay. Now from where we can get this 1,4 diketone. So we have to carry out another. We have to carry out like we have to think further for this retrosynthesis to from where we can get this 1,4 dicarbonyl compound. So basically functional group interconversion, right? Functional group interconversion of this alcohol to ketone. Okay, so simply by doing oxidation we can this carbonyl compound. Now from where we can get this alcohol. Okay, so if we do this CC1 disconnection. Okay, so this CC1 disconnection mean if we like how we are disconnecting. So basically this left hand side should be delta negative, sorry, delta negative, and right hand side should be delta positive, right? So this delta negative mean isopropyl, not isopropyl, so isopropyl with another carbon chain. So this is basically uh, isobutane. Okay, isobutyl anion. Okay, so isobutyl anion is the synthon for this disconnection approach, and this having positive charge, that is the acceptor synthon for this disconnection approach. So isobutyl anion it is the synthon. Okay, so from where we can get, so we can easily get from this Grignard reagent. So this is the isobutyl magnesium bromide. Okay, isobutyl magnesium bromide, and this is the aldehyde. So this is the reagent, and for this right hand side part, so this is the synthetic equivalent. Okay, so for acceptor synthon, so this is the acceptor synthon this side. So for acceptor synthon, this is the synthetic equivalent. Now from where we can get this synthetic equivalent, this aldehyde, how we can get? So we can get from this olefin, right? So from olefin, how we can get? So basically we can get in many ways. So if we do ozonolysis of this double bond, we can get aldehyde. Or if we convert this double bond to diol by using osmium tetroxide and then treat with NaIO4, then we can get the cleavage of diol and we can get this aldehyde, right? Very simple. Now how we can get this compound? So if we do this disconnection approach, right? This CC1 disconnection approach. So now this is next to carbonyl compound. So you can easily generate enolate, right? So enolate from where? So this carbon you can easily generate negative charge. So delta minus this carbon, right? And so enolate you can easily generate, and this carbon is having positive charge. So this is the delta positive. So this carbon is having delta positive mean you can have this allyl bromide. So this is basically allyl bromide. So CBr bond. So this C can have, this carbon can have this delta positive charge. Okay. So basically you have to mix this. You have to take this carbonyl compound, and if you generate the enolate, and that enolate if you treat with this allyl bromide, you will get this compound. Okay. Now, what about this Grignard part? So we that Grignard part we can get easily get from this isopropyl. So this is the isopropyl. So this if you have this bromine, okay, this bromine, you can easily generate the Grignard reagent from this alkyl bromide part by treating with magnesium. Okay, now coming to the so in this retrosynthesis, so how many steps are there, right? So first step is aldol reaction, second step is functional group interconversions to get this ketone, and so this alcohol how we can get? So basically, alcohol, so that we are doing this CC1 disconnection. So this left hand side part can be derived from this Grignard reagent, and this right hand side part, so this is the right hand side part is acceptor syntone. So carbocation at this carbon, okay. So acceptor syntone can we can easily get from this synthetic equivalent, so this aldehyde, okay. Now how we can get this aldehyde? So if we have the double one here, so this double one olefin, and if we do ozonolysis we can get uh, this aldehyde, or we if we treat this olefin with osmium tetroxide and NaIO4, then we can easily get the diol, right? Diol followed by diol cleavage to get this aldehyde, and this compound we can easily get from the enolate derived from this carbonyl compound, and electrophile we have to use this allyl bromide as a electrophile. Okay, so this is how we can plan this retrosynthesis. Now, um, what is the forward synthesis? Forward synthesis is very interesting. So first we have to take this compound. So this is the carbonyl compound, and if we take this carbonyl compound and treat this carbonyl compound with LDA, so LDA is so LDA. If you want to see the structure, so it is basically lithium isopropyl amide. Okay, so this is N minus, N minus, and Li plus. So this is strong base. So this is bulky base as well. So and this LDA also you can prepare. Okay, sometimes LDA is commercially LDA also of course commercially available, but you can also prepare in lab also. Okay, how? Now you have to take diisopropylamine. Basically LDA mean this diisopropylamide, right? So if you take diisopropylamine, so this NH and diisopropyl. So diisopropylamine called as DIPEA. Okay. So commercial name is DIPEA. So DIPA. So if you take this compound, now how you will generate this LDA? So if you treat this compound with N-butyl lithium, okay. So N-butyl lithium. So this carbon is having negative charge and Li plus. Okay. So N-butyl minus. So that will take the proton from amine. Okay. So it will generate N minus and the corresponding. So that will generate N minus and corresponding counter cation is Li plus. So N minus Li plus. So that is the LDA. And also after taking proton, this will generate N-butane. So N-butane is basically gas. Okay, so it is gaseous species. So you can easily generate LDA from this N-butyl lithium and diisopropylamine. Okay, so very interesting. So and if you treat, so this is basically bulky base. So if you treat this base with this compound, so this is basically carbonyl compound and having one acidic proton, right? So this LDA will abstract this proton, and it will generate the corresponding enolate. So basically enolate is lithium enolate. Okay, the corresponding counter cation is lithium. Now, after generating this lithium enolate, um, it can now this carbon, so it can acts as a nucleophile, right? So it will fall here. So this oxygen O minus will fall here, and this carbon, so this enolate will attack now to this electrophile. So so allyl bromide is here the electrophile, and you can easily get this CC bond. Okay, this CC bond you can easily get. So now you got this compound. So you are having this olefin. So what you have to do now? So you have to do. So you have to you need to get this aldehyde, right? So basically you can do ozonolysis. Otherwise, we can convert this olefin to diol first by using osmium tetroxide. I guess all of you know how osmium tetroxide can convert olefin to diol, right? So now, so this diol is, so you can make this diol. Now you can convert this diol to aldehyde. So by treating with NaIO4, so next if you use excess amount of NaIO4, so you will get the 1,2 diol cleavage. Okay, so basically 1,2 diol will get cleaved by using this NaIO4. Okay, so this is one name reaction, Lemux Johnson oxidation. Okay, so Professor Samik Nando, he told about this reagent in in week 1 third lecture, most probably. So he has mentioned about this reagent. So most of you know the reagent, what does this reagent, what osmium tetroxide and NaIO4. So the combination of this osmium tetroxide and NaIO4 says oxidative cleavage of this diol, so known as Lemux Johnson oxidation. Okay, so now you got this aldehyde, right? So what is the next part? So what you have to do now? So uh, we have to form this CC1. Okay, so how we can get? So basically, if we take this Grignard reagent, so already I have shown in the last slide this Grignard reagent how you can prepare. So this basically, if you take this bromine, alkyl bromide pieces. Okay, so this is isobutyl bromide. If you take this isobutyl bromide and if you treat this isobutyl bromide, already we discussed, if we treat with this magnesium, then we can get this RMGBr, right? So that is a Grignard reagent. So you can generate this, you can prepare this Grignard reagent, and then after preparation you can add this Grignard reagent to this aldehyde, right? And you will get this alcohol. After workup you will get the alcohol, right? So now after getting this alcohol you can do the oxidation by using PCC in DCM. DCM is solvent, PCC is the reagent to oxidate to do the oxidation of this alcohol, secondary alcohol, and you will get this ketone, right? And again, like last compound, uh, how we can get this alpha beta unsaturated carbonyl compound. So basically, if you do this is 1 2 3 4 for diketone. If you do the aldol reaction, so first you will get this beta hydroxy alpha beta hydroxy. First you will get this beta hydroxy alcohol, and then in same pot, so in reflux condition dehydration will happen, and you will get this olefin, right? So this is how you can get the target product. Okay, so this is our target TGT. So this is how you can plan for retrosynthesis for any target molecule by logical disconnection approach, and then you can do the forward synthesis by yourself. So this is very easy if you know the converse, most of the name reaction or many conversions. You can easily plan the retrosynthesis as well as forward synthesis. So this is nice, really nice. Also, if you practice the retrosynthesis, you can increase your knowledge more. Okay. So thank you. So if you have any doubt or queries, you can ask, right? If people have any doubts, you can ask me. Hello, or it is crystal clear. You can give feedback so that I can improve also, right? So did you get? Please respond. Any doubts? I guess no doubt. No doubt. Okay, just yeah. So this is my YouTube channel. So I have uploaded the recorded video of last lecture in this YouTube channel, right? So you can easily get this recorded video from this YouTube channel known as name as Anirban Mighty. So you can take screenshot and later you can do search. Also uh, this week lecture also I will upload in the same channel, so you can follow. If you forgot anything, you can revisit this YouTube link, and you can get access to this recorded video. Okay, thank you. So if you don't have any doubts, I'll stop today, and I'll come to next week, and I will discuss more complex examples, so that you can get more ideas about retrosynthesis, right? Yeah, thank you.